Someone was pointing out to me that every day from the 20th to the 29th is a palindrome. 4/25, 24, 4/26, 24, 4/27, 24. But I pointed out to them, if you include the whole year, then really only 4/20/2024 is the true palindrome. Anyway, not important. I like dates and stuff. All right, got a lot of things to talk about today, but that's always true in this class because lots of things to cover. Let's talk a little about area under a curve. Also, before I get going here, I have ideas about what I want to talk about. Are there things you want to see, specific questions you have? I know Hemmer-Galiava's class is a midterm on Monday, right? So if there's questions from those folks as well, I'm happy to address them. So if there's anything you want to see, you can say now, you can ask later.
That's the word problem.
Cool. That's exactly what's on my plate right here. Great.
Finding area or like between.
Yes.
With respect to.
Definitely. You guys are saying all the right things. I mean, not that there's wrong things to say, but you're saying all the things that I have already planned to talk about. So that's great. Can we see type 2 improper intervals? Sure. We did do, yeah. So we can start there actually, because that's where we kind of ended off last class. Yes. And when you say type 2, I'm imagining you mean the ones where it's not with an infinity or a negative infinity, where it's like undefined somewhere. I think that's what we're usually type 1 is the infinity type. Type 2 is the not infinity type. And again, I haven't seen, at least for Dedella's class, I haven't seen the homework problems on that. I don't know if that's going to change or not, because certainly there's no homework problems like that in the textbook. Have you all gotten the discussion sheet for this week for Dedell? Okay, I'm just curious. I'm curious if he has any type 2 improper intervals on that discussion sheet. Let's look at a couple examples though. So here's some type 2 improper intervals. Do a couple of them. So let's say we had the integral from 1 to 7 of 4 over x minus 5 to the 6th power. So first of all, we see that this is improper because we notice that the function that we're integrating is undefined where? At 5. And 5 is in the interval of integration. If this interval was from like 1 to 3, not improper. You just do it the normal way where you find the antiderivative, you plug in the endpoints and so on. But since the interval includes a place where that function is undefined, we have to use an improper interval setup. So we're going to first break this up as the integral from 1 to 5 of 4 over x minus 5 to the 6th, plus the integral from 5 to 7 of 4 over x minus 5 to the 6th. Personally, I'm a fan of dealing with each of these one at a time, because if one of them diverges, you don't really have to deal with the other one. So I'm going to deal with the first one. Say, okay, great. This first one here, I'm going to rewrite this as the limit as b approaches 5. You all should figure out which side of which side of 5 we're approaching from. The integral from 1 to b, and I'm going to rewrite the integrand as 4 times x minus 5 to the negative 6th power. All right, we're approaching 5 from the left to the right. From the left, because we're between 1 and 5. And then we're going to do the antiderivative. We're going to have the limit as b approaches 5 from the left of the antiderivative of 4 times x minus 5 to the negative 6 is going to be 4 times x minus 5 to the negative 6 plus 1 divided by negative 6 plus 1, which is negative 5. Nothing else needs to happen here because so you might notice I'm skipping the u substitution. Technically, you could do a quick little u sub, let u equal x minus 5. Your du would exactly be dx to essentially be integrating 4 times u to the negative 6. But really, I think we can get away without showing that work because it's really a straightforward u sub here. So then we're still evaluating from 1 to b. Here's what I know is going to happen. I'm going to plug in b and I'm going to plug in 5 for b. And I'm going to get 0 to a negative power. I don't like that. I would rather have my 0 raised to a positive power because it makes more sense to me. So I'm going to re-express this as the limit as b approaches 5 from the left of negative 4/5 times 1 over x minus 5 to the positive fifth from 1 to b, and then plug in my limits of integration and get the limit as b approaches 5 left of negative 4/5 times 1 over b minus 5 to the fifth. Minus a minus is plus 4/5 times 1 over 1 minus 5 to the fifth. And now we're going to observe that if you let b approach 5, 5 minus 5 is 0. 0 to the fifth is still 0. And you get the 0 in the denominator, means your fraction is blowing up to either infinity or negative infinity. If we want to be extra specific here, we could figure out that b is approaching 5 from the left, so we're less than 5. So less than 5 minus 5 is slightly negative. A slightly negative number to the fifth power is still negative. A negative number times a negative number is a positive number. So this part here is going to positive infinity. And then this part here is subconstant. So we end up with this portion of your improper integral diverging to infinity, and then we don't care what happens with the rest because the whole thing's going to diverge. I will say, if someone were to ask you, does this diverge to infinity or to negative infinity, or we don't know, then you would actually have to do the other half of this and find out that this other half also diverges to positive infinity in this case. And so the two infinities would add up to positive infinity. But if they ask, usually we don't ask that question. So that's why I'm not going to, usually we just like, does it diverge or converge? Great. If it converges, tell me what it converges to. If it diverges, just tell me it diverges. How would we do it if it's undefined at one of the bounds? So I would point out, this version is what I would say is actually the harder version, because you have to see where it's undefined and it's in the middle. If it's not one of the bounds, we kind of start off in the situation already. So let's look at another example. Let's look at, say, the integral from, I don't know, 1 to 10 of 6 over the cube root of, sure, 10 minus x dx. And this one, let's say 2 to 10, just so the numbers aren't quite as terrible as I wanted them to be. This function that we're integrating, this integrand, we can see is undefined when x is equal to 10. So 10 is the problem. As I mentioned before, you can only deal with one problem at a time. So if someone gave you something really unfortunate where you had two different places where the denominator was 0, you'd have to break it up at both those places. It's kind of terrible. So usually you're not going to see something quite so terrible. So here we're going to rewrite this as the limit. I should have made it the lower limit, but well. As b approaches 10 from the left of the integral from 2 to b. And I might as well rewrite my integrand in a way that's easier to anti-differentiate. So I'm going to think of this as 6 times 10 minus x to the negative 1/3. I, again, think we can get away without actually writing down the u sub here. So I know that if I integrate u to the negative 1/3, it's going to be u to the negative 1/3 plus 1 divided by negative 1/3 plus 1. So we're going to be getting here the limit as b approaches 10 from the left. The 6 hangs out. The antiderivative of 10 minus x to the negative 1/3 is going to be 10 minus x to the positive 2/3 divided by positive 2/3 is like multiplying by 3/2. And what else do I need to divide by? Thank you. Yes, -1, because the coefficient of x here is -1. I'm just going to put the negative out in front though, because dividing by -1 is equivalent to multiplying by -1. And then we would have the limits from 2 to 10. Sorry, from 2 to where? 2 to b. And then we plug in, we get the limit as b approaches 10 from the left. -6 times 3/2 is -9 times 10 minus b to the 2/3 minus -9 times 10 minus 2 to the 2/3. And in this case, when we plug in what b is approaching, you still get 0, but you get 0 to a positive power. And 0 to a positive power is just 0. I don't like to think about 0 to a negative power being undefined. I would rather say 1 over 0 to a positive power is 1 over 0, which is undefined. But here we're gonna be getting -9 times 0 plus 9 times 8 to the 2/3 power. And 8 to the 2/3 is 4, because it's the cube root of 8, which is 2, squared, which is 4. So you get 9 times 4, which is 36. So this integral converges to 36. Might as well add some spice to this question. Extra. What is the average value of this function, f of x equal to 6 over the cube root of 10 minus x, on this interval? That's kind of cool. I kind of like that. Well, average value is great. Great's not the right word. Average value is easy. If you know how to find the area or the definite integral, the average value is literally a one-step tiny little thing you do. The average value here is going to be the same integral we just found, divided by what? The length of the interval. So whenever you're finding average value, it's just your definite integral divided by your b minus a, which in this case is 8. So my average value here is going to be 36 divided by 8, which we could reduce to what? 9 over 2, which is 4.5. So if you know how to find definite intervals, you know how to find average value, just dividing by the length of the interval. We'll look at that a little bit more in depth. In depth is not the right word. We'll look at it a little bit more later on, just to kind of clarify what we're getting when we do that. All right, question.
Why was in the other one when you did from 7 to 1? Why was when you plugged in B, why did you go to positive and make sure and plugged in B here over here?
Good question. So here, when I plugged in B, I had 5 minus 5 in the denominator. So 0 to the 5th is 0, but 1 over 0 is a really, really large number. Really, when I say 1 over 0, I'm not thinking 1 over 0. I'm thinking 1 divided by a super duper tiny number, like 1 divided by 1/1,000,000th. But 1 divided by 1/1,000,000th is the same as 1 times 1,000,000 over 1. So that's why. I will point out some people would do it like this and say you had like b minus 5 to the -5th and then get 0 to the -5th. And it's really, really easy to accidentally incorrectly convince yourself that 0 to the -5th is 0. Not 0 to the -5th is 1 over 0 to the 5th, which is 1 over 0, which is undefined, which is blowing up to some sort of infinity. Which is why I would encourage you to write it as a positive power, not a negative power. Cool. Let's look at some more area stuff.
I also have a question. Sorry. I'm just not sure I understand why on the most recent problem that you did with the 10, why 10 minus b is 0.
So technically here I could have actually plugged in b. I wasn't showing that work, but what I'm really doing here is I'm getting, right, when we evaluate limits, often the way we do them is we just plug in whatever b is approaching. So I could have written here that this is -9 times 10 minus 10 to the 2/3 plus 9 times 8 to the 2/3. So I'm just doing the thing we often do with limits, which is plug in whatever b is approaching. And then 10 minus 10 is 0, and 0 to the 2/3 is still 0.
Oh, okay, I guess I got confused. Thank you.
You're welcome. All right. Let's look at, yeah. So let's say we want to, so we'll set up, maybe we'll definitely set up. We want to set up the integral or integrals for the area bounded by the curves y equals x squared, y equals 1 over x, and y equal to 9 in the first quadrant. And although it's not required, it is often very, very helpful to draw the graphs. So I'm going to try and draw these. We have some decent ideas of how these things look. So y equals x squared is your usual parabola kind of thing. Something like that. And y equal to 1 over x is your usual hyperbola. That's the hyperbola. Kind of like this. At least the right side of it does. And y equal to 9 is just a horizontal line. So I'm looking at this region here. And I'm trying to find its area. So typically, at least from the beginning, when we start off trying to find area, we usually think about adding up a bunch of rectangles. So I'm imagining here a vertical rectangle like this. And at least for the rectangle I've drawn currently, the area of that rectangle is equal to the base times the height. The height is the top function minus the bottom function. So it's going to be 9 minus 1 over x. And the base of that rectangle is a small change in x, a dx, or a delta x. However, because of the situation, the region I have here, if I drew my rectangle further to the right, like over here, you might notice that the top boundary is still y equals 9, but the bottom boundary is now y equals x squared. So for this other rectangle I've drawn in blue, I know it's probably hard to see the actual colors I'm using, but for the second rectangle, its area is a height of 9 minus x squared times the base of dx. And so the issue with doing it this way is that we end up having to use two integrals. So we're going to say that the total area is equal to, well, I'm going to break it up right here. So that over here, I'm using rectangles where the height is 9 minus 1 over x. And to do that, I have to integrate from whatever this value of x is to whatever that value of x is. I'll figure that out in a second here. Of 9 minus 1 over x dx. Okay, let's find this point. So to find this point here, I'm going to set the red function equal to the green function. So I'm going to set 1 over x equal to 9. I can take the reciprocal of both sides and get x equal to 1 over 9. That's going to be my lower limit of integration. And then to find this point of intersection here, I'm going to set y equals x squared equal to 1 over x. And I guess I would just, multiply both sides by x. You get 1 equal to x cubed. And if 1 is equal to x cubed, x has to be 1. And I might as well find this point over here too. So if I set x squared equal to 9, I'm going to get x equal to plus or minus 3, but I know I'm on the right side of the y-axis, so I know that x is positive 3 here. So for this first integral that's giving me this area here, I'm doing the integral from 1/9 to 1 of 9 minus 1 over x. Plus this second area here I'm going to get by doing the integral from 1 to 3 of, again, the top function minus the bottom function, which is now going to be 9 minus x squared dx. And yeah, we might as well find the area here. It's going to be a little bit gross, but we should do it anyway. So calculating it, we're going to get, so for this first integral, we get 9x minus the natural log of the absolute value of x, evaluated from 1/9 to 1, minus, over here, we're going to get 9x minus x cubed over 3, evaluated from 1 to 3. And then we plug in, we get 9 minus natural log of 1. Natural log of 1 is 0. Minus, plug in here, 9 times 1/9 is 1. Minus natural log of 1/9. Minus over here, we're going to get 9 times 3 is 27. Minus 3 cubed is also 27. 27 divided by 3 is 9. Minus, plug in 1, you get 9 minus 1/3. I don't really care to simplify that. And this, although not terrible, might not be as easy as we could make it. So let's point out that while you could do it this way, you could also do it using the variable y. You could use horizontal strips instead of vertical strips to imagine what's going on here. Let's draw this again. Same here. Cool. So we're still looking at the same region, but now we're going to try to make it easier in the sense that we only really want to use one integral. And most people, if they have the choice, most teachers, if they have the choice, are going to default to wanting to write things in one integral instead of two. So here what we can do is we can draw a horizontal strip. And imagine that the area of our strip, I'm going to start saying strip instead of rectangle, I think, is going to be, well, again, it's base times height. Or I would really say, I guess I would say base times length here. I'm always imagining the base is like the little teeny width there, width times length. So the width is that, the length is that. The area of my strip is the length times the width. And unlike before, instead of the length being the top minus the bottom, now the length of that strip is going to be the right function minus the left function. That's going to be right minus left. And the width of this rectangle or this strip is a small change in y. So it's a dy. And if you're using a dy, that means you have to write your functions in terms of the variable y. So we can't say, in fact, we can't say we're going to have the right function, which is y equals x squared, minus the left function, which is 1 over x times dy. That's not going to work for us if we try to integrate that because we got the wrong variable. So we have to change all our functions. This y equals x squared is going to become x equal to plus or minus the square root of y. But again, since we're on the right side of the y-axis, we know that x is positive. So x is the positive square root of y. I will mention that over here, x would be equal to the negative square root of y, because x is negative over there. Yeah.
Like the hard part of this one, just like what if it's not super detailed and visualize like that?
That's a good question. It really, I would say the way we usually do these is by getting some sort of, it doesn't have to be a perfect graph, but you do need to be able to get some sort of graph of the thing. I think it's really the easiest way. Usually with these functions, usually the graphs are not super terrible.
Okay, I guess
That I mean, you're right to ask that question, but so I would say if you've got more than two functions going on, more than two boundaries, typically they're not terrible or too terrible, and typically they're relatively easy to graph. If you only have two functions, we'll talk about it more in a second, usually you can get away without graphing them. So let's, sorry, I was going to find, the left boundary here is, it was y equals 1 over x. The funny thing about this is when you solve for x, you get the same kind of thing. You get x equals 1 over y. So you get x equals 1 over y. In fact, 1 over x is one of the few functions that is its own inverse function. It's kind of neat. So instead, we're going to say not that. We're going to say that the area of our strip is actually the right function, square root of y, minus the left function, 1 over y, all multiplied by dy. And then my total area is where we add up all the strips, all the areas of the strips, I should say. So we're going to do the integral from as low as, well, the x value is 1, the y value is also 1, to as high as a y value of 9 of the right function minus the left function. And to me, that looks a little less terrible to integrate. We integrate this, we've got y to the 1/2, so the antiderivative of y to the 1/2 is y to the 3/2 times 2/3. The antiderivative of 1 over y is the natural log of the absolute value of y, evaluated from 1 to 9. So we're going to get 2/3 times 9 to the 3/2 minus the natural log of 9 minus 2/3 times 1 to the 3 halves. 1 to any power is 1. So 2/3 times 1 to the 3 halves is just 2/3 minus the natural log of 1 is 0. And I would say the nice thing about doing it this way, you kind of get a more simplified answer from the get-go. 9 to the 3 halves is 27. 2/3 times 27 is 18. So you get 18 minus the natural log of 9 minus 2/3. Which might look a little different than our other answer, but I will tell you, if you do enough simplifying, the answers are the same. I mean, the answers are the same whether or not you simplify. But if you do enough simplifying, you can show that they are the same. Okay. Yeah, let's do that. Questions? Yeah. Mm-hmm.
Like just a normal, like, lower number on the bottom.
So I'm really looking at the region and I'm seeing, oh, that y value there is 1. And that top y value is 9. That's all I'm seeing what the limits of integration are. But again, I'm really getting it from the graphing. Let's look at another example where we wouldn't necessarily graph it. Yo, question. Yeah.
So always like the bigger number on top, no, right?
Typically, yes. Yeah, if you're writing a definite integral that is representative of an area that you've found, yes, it's almost always the upper limit is the larger value and the lower limit is the lesser value. I can't think of a reason why you wouldn't write it that way. At least for representing an area. Okay, let's say we wanted to find the area between the curves. Sure. Y equal to the square root of 2x and y equal to x. And we didn't want to draw it. Well, as long as it's just two curves, you can usually get away without drawing. So the first thing we're going to do is find the points of intersection. So set the two functions equal to each other. So x equals the square root of 2x. I'm going to square both sides. I'm going to get x squared equal to 2x. I'm not going to divide both sides by x because that's dangerous. I'd lose the solution. I'm going to bring everything to one side, and then I'm going to factor. So x squared minus 2x equals 0. You get x times x minus 2 equal to 0. So our points of intersection are going to be x equal to 0 and x equal to 2. So I know that my area is going to be the integral from 0 to 2 of the top function minus the bottom function. Now, if you really, I don't like saying this, but I'll say it. If you really don't want to find the top or the bottom, you can just say, I'm going to just subtract it whatever way I want. And then if the answer comes out negative, I'm going to put absolute values around everything. So one could say, let me make the wrong choice here. One could say the area is equal to the integral from 0 to 2 of x minus the square root of 2x. And then anti-differentiate that and get x squared over 2 minus, so I've got 2x to the 1/2. The integral of 2x to the 1/2 is 2x to the 3/2 times 2/3 divided by 2 because of the 2x there. So really you're getting 1/3 times 2x to the 3/2. From 0 to 2, we plug in, and you plug in 2, you're going to get 4 over 2 minus 1/3 times 2 times 2 is 4 to the 3/2 minus 0 minus 0. And then if we simplify this, we get 4 over 2 is 2. 4 to the 3/2 is the square root of 4 cubed, which is 2 cubed, which is 8. 8 times 1/3. And 8/3 is bigger than 2. So if we do with one more step, we're getting 2 minus 8/3, which is 6/3 minus 8/3, which is negative 2/3. But we know an area shouldn't be negative. So at this point, I would go back and say, okay, the area is the absolute value of this, which 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 is 2/3. And that is valid. And I don't like it. But it's fine. If you want to do it this way and your teacher's okay with you doing it this way, it's a legitimate way of doing it. But for me, the way I would have done this instead would I would have said, okay, well, my area is going to equal the integral from 0 to 2 of the top function minus the bottom function. And then to figure out which one is the top function, well, one of my functions is y equals x. One of my functions is y equal to the square root of 2x. Pick any point between 0 and 2, or between whatever your limits of integration are. The obvious choice here is 1. If you plug in x equal to 1, that one you're going to get y equal to 1. That one you're going to get y equal to the square root of 2. Which is bigger? Which is bigger? 1 or the square root of 2? Square root of 2. So that means that function is the top. So then we do the integral from 0 to 2 of the square root of 2x minus x. I will point out, if you don't like the way I integrated the square root of 2x, and I would not feel bad about that, the easier way to do that is to actually break the square root of 2x apart as the square root of 2 times the square root of x. Then the square root of 2 is just a constant that hangs out. Square root of x is x to the 1/2, and we can integrate this as, I'm integrating it. I shouldn't write the integral symbol. I guess I'll do one more simplification there. Cop out. And then we're going to integrate and get square root of 2 times x to the 3/2 times 2/3 from 0 to 2. Oh, minus, not from 0 to 2 yet. Minus x squared over 2 from 0 to 2. And then you would plug in and you would get the same answer of positive 2/3. This one's a little bit less nice though, because if you do it this way, you get the square root of 2 times 2 to the 3/2 times 2/3 minus 4 over 2 minus 0 minus 0. And figuring out that this is actually nice is a little bit wonky. So you might rewrite this as, oh, that's 2 to the 1/2 times 2 to the 3/2, which is really just 2 squared. You really got 2 squared, which is 4. So you really do have 8/3 minus 2, which is 2/3, same answer. So lots of ways to go about doing these things.
Where did that square root come from?
The square right here.
Yeah.
So there's a rule about square roots that says if you have the square root of a product of two positive numbers, you can always break it apart as the square root of a times the square root of b.
Oh, okay.
Yeah. Like, for example, the square root of 4 times 9 is the square root of 36, which is 6, but it's also the square root of 2 times the square root of, the square root of 4 times the square root of 9, which is 2 times 3, which is 6. So either way you can do it. It doesn't work if you have negatives, though. It's kind of wonky if you have negative stuff in there. So you don't use it when you have positive things multiplied together. All right. Sure, let's do one more thing there. So let's talk for just one more second about average value, and then we're going to kind of move into some of these word problems. So let's say we want to find the average value of f of x equal to 3x squared on the interval from 1 to 3. So what I want to point out, sorry, this is one piece of paper here that's killing me. What I want to point out is the computation for average value is really not terrible, right? You can find this average value really easily by saying, well, you're going to get the average value equal to the integral from 1 to 3 of your function divided by 3 minus 1. But what I wanted to say more about really was just what the idea of average value really is. So if we graph this function, 3x squared, it's going to look something like this. Sharper chart. So here's my y equals 3x squared. And if we're looking at the interval from 1 to 3, so what we're doing is we're saying, well, essentially, if you took all that area and flattened it out so it was all the same height, but you still have the same amount of area, that height would be the average value. Also called the average height of a function. Average value, average height, same thing. So the idea here is that, in fact, let's actually find it before we say what it is. So if you calculate this, the antiderivative of 3x squared is x cubed from 1 to 3, divided by 3 minus 1. And then x cubed from 3 to 1 is going to be 3 cubed minus 1 cubed divided by 2, which is 27 minus 1 divided by 2, which is 13. I'll point out that this function, if you plug in 1, has a y value of 3. You plug in 3 has a y value of 9 times 3, which is 27. And 13 is somewhere kind of in the middle-ish, maybe a little closer. I don't know, it's close to this, it's a little bit lower. So maybe 13 is about like right, I don't know, there. So we're saying is if you took all this area and put it in a rectangle of height 13, this area in red would be the same as the area in blue. I've often thought about it. A student explained to me one time so first of all, you all know what an ant farm is, right? You had like this green, I had one when I was a kid, there's a green thing, you put like white rock sand in it. And if you had an ant farm with some limited width, maybe all the sand looked like that, right? But if you shake it up and level it all out, same amount of area, but now it's all at whatever the average value or the average height of that function would be. That's kind of the idea, is that you're finding where everything levels out. That's probably too low for the average value of that. But you get, so hopefully that kind of clarifies the idea, right? This area would be the same as the area under my mountainous looking curve there. Let's do some word problems that have this idea. Try and keep my paper just somewhat in order here. Yeah, maybe. Sure. So this problem, just so you're aware, is similar to number 18 in section 6.2. Not exactly the same, I don't think, but similar. So there's a lot of words here. For a fish that starts life with a length of 4 centimeters to 4 and has a maximum length of 29 centimeters, the von Bertalanffy, however you say that guy's name or woman's name, I don't know, growth model predicts the growth rate, note the word rate there, is L prime of A equal to 25e to the negative A centimeters per year, where A is the age of the fish. And now finally, after all that buildup, the question, find the average length of the fish for the first 5 years of its life. Okay. So I want to point out, they didn't give us the length as a function of age. They gave us the rate of growth of the length as a function of age. So, right, we were given L prime of A, not L of A. So if you're given a derivative and you're trying to find the function, what do? Anti-differentiate or integrate, right? Either way, same thing, right? Those words mean the same thing to us. So to find the length as a function of A for the first 5 years, we're going to do the integral from 0 to 5 of 25e to the negative A dA. Now this is going to be kind of funky because, well, check it out. When we integrate this, and I feel like there's something a little interesting here. I feel like I actually want, I don't want that to be a 5 just yet. Yeah. So I want that to be So I'm kind of doing something a little bit shady here, but fine, we'll live with it. We'll make that an A. Then we integrate this, the integral of 25e to the negative a is 25e to the negative a divided by -1. And we're evaluating from 0 to a, so we're plugging in the a. And we're getting -25e to the negative a. I don't love the way I've written this. I apologize. What I really should have just said is I should have not done the definite integral yet. I'm going to scratch this out because I feel bad about it. What I really should have just said is that L of a is the indefinite integral of 25e to the negative a, which is going to be -25e to the negative a plus c. And the reason we need to do this is because we are given some initial condition that's just kind of hiding in the problem. So we're told that in the beginning, the fish is how long? And that's the maximum length it's going to get to. How big is the fish when it's born? 4 centimeters. So we know that L of 0, the length at time 0, should be 4 centimeters. So we're going to set -25 times e to the 0 plus c equal to that initial value of 4. And then we're going to solve for the constant c. So we're going to get that c is equal to 4 plus 25, which is 29. It is not a coincidence that c happens to be the maximum value here. Because if you were to take the limit as a goes to infinity of this expression, this would go to 0. And so as time goes on and on and on and on, we're going to get closer and closer to that 29 centimeter maximum length. So that's why it's not a coincidence that c is 29. It is actually by design that c is 29. So then what we're going to say is the length at age a is going to be -25 e to the negative a plus 29. So now that we've got the length, to find the average length of the fish over the first 5 years, we have to integrate that function. Right? This is the length at time t, time a. So to find the average value of length, I want to go back and point this out, right? They really did give us the growth rate and then asked us to find the average length of the fish. So to find the average value of something, you're finding the integral of that function that represents that thing. So since they said find the average value of the length of the fish, we have to integrate the function that is the length of the fish. So we're having to do integrals twice here. First, we had to integrate to find the length function. Now we're going to have to integrate that to find the average value. So the average value of the length is going to be the integral from 0 to 5 of our length function divided by the length of the interval, or the length of the number of years, which is just 5 minus 0. That's going to be the 1 over 5 times the integral from 0 to 5 of the function we just found. -25 e to the negative a plus 29 dA. So then we integrate this again. We get 1 over 5 times the integral of -25 e to the negative a is going to be +25 e to the negative a. And the antiderivative of 29 is going to be 29a from 0 to 5. And then we plug in, we get some not particularly lovely numbers. We get 1/5 times 25 e to the negative 5th plus 29 times 5 minus, we plug in 0, you get 25 e to the 0 plus 0. And you could simplify this more if you really wanted to. That's going to be 1/5 times 25 e to the negative 5th. 29 times 5 is 145, minus 25 is going to be 120. And if you really wanted to, you could get out a calculator and say it's going to be approximately 24.03 centimeters. Interesting. Grows a lot in its first few years. Question? Yeah.
Oh, wait, no, never mind. I think that 1/5 is just coming from the B minus A right there.
Yep, exactly. That's the one, or that divided by 5 minus 0, I rewrote as times 1/5.
Like, I know when we crossed out, right? Like zero,
Right.
But like that, but then like mine.
Right. So the problem is, if we just done the integral of the function that they gave us, you're integrating the growth rate, and that's just giving you the length. So you're essentially taking just the length of the fish, not how much the length has changed, and dividing it by 5. And that'd be incorrect. So, right, because, so again, it's these words here. So they said, find the average length of the fish. So to find the average length, find the average of a function, you do the integral of that function and divide by b minus a. Right, but they didn't give us that function. They didn't give us the length function. They gave us the rate of change of the length function. So we had to first anti-differentiate that function to get the length function, and then having the length function, which was what I wrote up here, right? So I'll point out, right? L of A is that, and the L prime of A was negative 25 e to the, sorry, positive 25 e to the negative A, right? We weren't asked to find the average value of that. We were asked to find the average value of that. And so then we integrated that and divided by the length of the interval. And it's a little tricky. The words are not super straightforward. Yeah. Yes. So just like, so like right here, when I integrated e to the negative a, I got e to the negative a divided by -1 because of the coefficient of a variable there. Just like if you integrate e to the 4x, you get e to the 4x divided by 4. All right, let's look at some more word problem fun. What I got next? Yeah. Oh, I think I have a handout. Yeah. Cool. So here's a handout. We're going to work through this problem together. Not on handout. For those of you on Zoom, I'll post this handout later, but you don't really need the handout. It's going to be easier if you're not going to write down a million things. I guess I could do this more efficiently. Oh, yeah.
Sorry, I have to go to an advising.
That's fine.
But do you have office hours today?
I have office hours. So usual office hours I have in CADS from after class to 11:45, and then later on and drop in from 1 to 3.
Okay, that was.
You're welcome. So the handout looks like this. Survival, and I'm going to use the handout too because I don't want to write all this stuff down. So let's talk about the handout. Can I move papers? Maybe. So survival and renewal functions. And let's just read through this to kind of get an idea of what's going on here. Let's see if I can maybe focus here a little bit. Cool. So when we talk about survival and renewal, you've got this kind of model. We have a population begins with P naught members, and members are added at a rate given by the renewal function R of T, which might be a constant or might not be a constant. T, where T is measured in years. The proportion of the population that remains after 2 years is given by the survival function S of T. Then the population capital T years from now is given by this equation, which I never remember. I've seen this equation a lot of times. I've never memorized it. It just doesn't stick in my head. I don't think you need to memorize this equation, but if your teacher says you do, then you do. I don't think you do though. So here's the equation. The population at time T is equal to the survival function multiplied by the initial population. I should say the survival function evaluated at the end time, whatever T years happens to be, right? Capital T is not a variable. Capital T is just like how long we're doing this for. And then you're going to multiply that by the initial population. And then you're going to add the integral from year 0 to the end year times the survival function of capital T minus the variable T times R of T. That's a lot of stuff. Let's do the example. So insect survival and renewal. Population of insects currently has, this is making me think of the cicadas that are coming, like the super duper cicada. Like there's 2 different cicada things coming. My wife sent me this terrible link that I don't, no, I'm gonna tell you. Apparently they pee a lot. The cicadas pee, and they have like jet streams of pee. Like they're like nature's apparently most like most have like some of the most strong urine streams of any animal in nature. So people in the Midwest are going to get peed on by all the cicadas. It's like they call it morning dew, apparently. Anyway, back to the math. population of insects currently numbers 22,500. So that's our P naught. Let's write stuff down as we go. Sorry, I got off track there. And it's increasing at a rate of R of T. They told us what R of T was. Great. R of T is going to be 1,225 e to the 0.14 T insects per week. If the survival function for insects is S of T equal to e to the negative 0.2 T, where T is measured in weeks, how many insects are there after 12 weeks? So our capital T is 12. So now I'm literally just going to throw this all into this equation. So my P of 12 is going to be S of 12. So S of 12 is going to be e to the negative 0.2 times 12. Times P naught, which is 22,500. Plus the integral from 0 to 12. The S of T minus T, I think, is always where people get thrown off a little bit. The S of T minus T here is going to be S of 12 minus T. So we're going to say that's going to be e to the negative 0.2 times 12 minus T times your renewal function, which is the 1,225 e to the 0.14 T dt. Let's label these things just so everyone knows what we got here. This is your S of 12. This is your P naught. There's your capital T, which is 12. Here is your S of 12 minus T, and here is your R of T. So literally, whenever I do a problem like this, I just go look up the formula, identify what is what, and plug it all into this sort of thing. And then after that, that's where we have to do a little bit of work. Do a little bit of simplifying here. So we're going to get, let's see. I would rewrite this first part as 22,500 times e to the, let's see, 0.2 times 12 is going to be 2.4. So it's negative 2.4. Plus but before I write the integral, I'm going to pull out any constants. So I'm going to pull out the 1,225. There is another constant I can't pull out, but I'm going to wait on that for a second. So I'm going to simplify the integrand as e to the negative 0.2 times 12 is negative 2.4. Negative 0.2 times negative t is plus 0.2 t. And I also have an e to the 0.14 t. And I can certainly add those powers together. But what I really want to do is I want to write this as e to the negative 2.4 times e to the 0.2 plus 0.14 is 0.34 t. Because the e to the negative 2.4 is also just a constant. And I don't really need to think about it. I can pull it out in front of my integral. So I'm going to do one more simplification before I fully write this. I'm going to write this is equal to 22,500 times e to the negative 2.4 plus 1,225 times e to the negative 2.4 times the integral from, sorry, I'm running out of room here, 0 to 12 of e to the 0.34. So, yeah, no, yeah, 0.34, that's fine. T, dt. And then integrating e to the 0.34 is pretty straightforward. Sorry, integrating e to the 0.34 times t is pretty straightforward. We're going to get 22,500 e to the negative 2.4 plus 1,225 times e to the negative 2.4. I guess I could combine those together. Oh, no, I can't. No, that's a giant lie I just said. Don't listen to me. I can't combine those together. This is still multiplied by the integral there. That's a big no. And then the integral of this is going to be e to the positive 0.34 t divided by 0.34 evaluated from 0 to 12. Which ends up being something, which is approximately, if you plug it all into a calculator, 21,046 insects. Yeah.
How are you going to pull out the negative 2.4 again?
So what I did, and let me show that work a little bit more here. what I did right here was I said that I have, so just looking at this integrand here, I have e to the negative 0.2 times 12 minus t times, I'm pulling out the 1225 times e to the 0.14 t. And I can really write that as just e to the negative 0.2 times 12, so negative 2.4, negative 0.2 times negative t, so plus 0.2 t, excuse me, and plus 0.14 t. Right? Because if I add all these e to a powers, I can add the powers together. So I'm multiplying this out, I'm adding the powers together, but then I can break that apart as e to the negative 2.4 times e to the 0.2 t plus 0.14 t. And then I can break that apart as e to the negative 2.4 times e to the 0.2 times plus 0.14 is 0.34 t. But this is just a constant. I don't know what it is, but it's not a variable, right? E to the negative 2.4 never changes. It's always whatever terrible number it is, and I can just bring it out in front. You don't have to bring it out in front. We can always leave constants inside the interval if we want to. It just usually feels like easier if you bring it out in front, because then the thing that's left in the integrand seems like it's less terrible to deal with. Cool. Should we do another one? Yeah, we probably should. So the one thing I'll say about these survival renewal problems is it's really just reading the problem and making sure you're substituting the right things into the formula. And then the formula is usually not too awful. I mean, it's not the best, but it's not the worst. I know that's not high praise, but you know. Let's look at another example that I don't have a handout for. So let's see, where'd you go here? Maybe I do. Do I have another example? I said I had another example, and now it's like it's hiding from me. Maybe not. Let's take a look here. Not you, not you. Oh, there we go. That doesn't seem right though. Here we go. There it is. Yes. Okay. So here's another example of a survival renewal situation. Drug is administered intravenously to a patient at a rate of 10 milligrams per hour. We should probably think of that as being our R of t, right? It's our rate of, I forgot the words already. It's our renewal function. The patient's body eliminates the drug over time so that the proportion that remains, that's going to be the survival, is e to the negative 0.25 times t. If the patient currently has 70 milligrams of the drug in her bloodstream, how much is present 8 hours from now? So when I do a problem like this, I'm going to identify the 4 things I need to identify. I need to know what P naught is, the initial amount of stuff. We'll say P naught here is our 70 milligrams. I need to identify my renewal function. Well, we're getting 10 milligrams of drug every hour. So our R of T is just going to be 10. There's no variable attached to that. R can be a constant. It happens a lot. Our survival function, S of t, is e to the negative 0.25 t. And then our capital T here is 8 hours. I would also, since I've already got this here, I would probably take the moment just to write down that S of capital T minus little t is S of 8 minus little t, which is going to be e to the negative 0.25 times 8 minus little t. And 8 times 0.25 is 2. So you can really write this as e to the negative 2 plus 0.25 t. if you wanted to. All right, so now that we've got all the things, we're just gonna set up the formula. So it's gonna be P of 12 equal to S of 12 times P naught plus the integral from 0 to 12 of S of 12 minus T times R of T dt. I didn't write out the formula as generically as I could have. I plugged in 12 for capital T. But then we're just gonna plug in all the things. So let's see. So S of 12 is gonna be e to the, why am I saying 12? Right, it's 8. I think 12 was the last problem, maybe. I don't know how I started doing 12. Sorry about that. Shouldn't be 12, it should be 8. You guys are like, why did you plug in 12? Good question. Sorry about that. Good thing 12 so easily turned into 8s. So then we get S of 8, which is going to be e to the negative 0.25 times 8, which is just e to the negative 2, times P naught, which is 70, plus the integral from 0 to 8 of our S of 8 minus T was e to the negative 2 plus 0.25 T, and our R of T was just 10. So I'm going to do the same sort of simplification I did last time. I'm going to write this in a way that I find more comfortable. Instead of writing 70 times e to the negative second, I would really rather write 70 divided by e squared. That just feels nicer to me. Over here, I'm going to pull out the 10. I'm also going to pull out the e to the negative 2. And have the integral from 0 to 8 of just e to the 0.25 t dt. So then we're going to get 70 over e squared plus 10 over e squared. And the integral of e to the negative 0.25 t, sorry, e to the positive 0.25 t is e to the 0.25 t divided by 0.25 from 0 to 8. Dividing by 0.25 is the same as multiplying by 4. So I'm going to rewrite this as 70 over e squared plus 40 over e squared times e to the 0.25 times 8 minus e to the 0. So there's our answer. Interesting here. All right, 1 second. Oh, no, that's fine. Yeah. Making sure I'm not seeing something weird here. Yeah, that's totally fine. And if we then, right, I mean, I would just leave it like that. Yeah, question.
40 over e.
Sure. So dividing by 0.25, 0.25 is 1/4. And so dividing by 1/4 is the same as multiplying by 4. So I multiplied by 4. All right. We end at 10:20, right? Yeah, okay. So while we could do more word problems, here's what I'll say about word problems. We could do more, but I think we shouldn't because I'm not going to see you all till Tuesday. And you're probably going to talk about volume. You're probably going to talk about volume either on Friday or on Monday. So let's do a couple volume examples just to help me prepare for that. I will point out all these word problems that I'm going over are on Grant's website, and he has written them out very nicely. And there's there's one on here about cardiac output. Oh, I should talk about that. There's one on here about what was the other one that I noticed? The blood flow thing that Dr. Liddell talked about in class yesterday. There's one on here about some other stuff. So there's lots of good examples and they're really written out nicely. So if you want more examples that you can read kind of easily, I would highly recommend going and looking at them. But I do feel like I should not leave you until Tuesday without you having seen at least a couple examples of volume. Yeah. Oh, you do? Okay. So we did do a couple in the beginning.
Harder one.
So I'm not good at knowing what feels like a harder one. Like I'm happy to just if you have one in mind, I'm happy to do it. But I guess I'm not sure what you mean by like harder. Like where you have to do like maybe U sub or iteration by parts first. Okay, let's see here. I feel like we've done something. Yeah, we can do one like that. Okay. So let's say for whatever reason, we had to find, do we want to converge or not? Sure, the integral from negative infinity to 0 of, sure, x squared e to the x dx. Yeah, that's terrible. Is that gonna be fine? That's gonna be fine. Okay, so what method of integration are we gonna have to use here? Is it u sub? Is it integration by parts? Is it something else? Good question. So it's definitely going to be integration by parts. And I really hate doing definite integrals with integration by parts. So if I was asked to do this, before I started doing any of the improper this, I would first do the indefinite integral, which is going to require integration by parts twice. We can do it the long way, we can do it the short way. I'm going to do it the short way because I have 13 minutes left. The short way being tabular integration, which does work for this type of integral. So that u equal x squared. My derivatives are going to be 2x and then 2 and then 0. My dv is super nice. It's e to the x, the antiderivative is e to the x, the antiderivative is e to the x, the antiderivative is e to the x. So my integral of this is going to be x squared times e to the x minus 2x times e to the x plus 2 times e to the x. And I don't care about the plus c. So the reason I'm doing that is so that then when I do all the improper limit as b goes to whatever, right? I don't have to carry all of that with by then doing integration by parts once or twice. So I'm going to think of this now as the limit as a approaches negative infinity of the integral from a to 0 of x squared times e to the x. And then I'm super happy because the next step, I can just rewrite it as the limit as a goes to negative infinity of my antiderivative evaluated from 0 to a. That's going to be the limit as a goes to negative infinity of my antiderivative, which is x squared e to the x minus 2x e to the x plus 2 e to the x evaluated from from a to 0. We plug in, make the limit as a goes to negative infinity of 0 times e to the 0. I really don't want to write it, but I will. It's like 0 times e to the 0 minus 2 times 0 times e to the 0 plus 2 times e to the 0, which is 2, minus, I have not left myself enough room here, a squared e to the a minus 2a e to the a plus 2 e to the a. It's terrible. Let me rewrite this down here. That's going to be the limit as a goes to negative infinity of 2 minus all of that. That a squared e to the a minus 2a e to the a plus 2 e to the a. How do we deal with that limit? Well, it's unfortunate. It is, what do we call that? An indeterminate form. If a is going to negative infinity, a squared is infinite, and e to the a is going to 0. If a is going, think about the graph of e to the x. If you're going way to the left, you're getting closer and closer and closer to 0. When you have a 0 times infinity, it's indeterminate. And if I were Dr. Dedell and asking you to do this, I would probably expect you to use L'Hopital's rule here. So here's how we're going to rewrite this. I think the easiest way is not to deal with each of these separately. It's actually to factor out an e to the a. So I'm going to write this as, watch, 2 minus the limit as a goes to negative infinity of the remaining stuff here, which I'm going to write as e to the a times a squared minus 2a plus 2. And I for sure can't use L'Hopital's rule yet, because I don't have a fraction. You have to have a fraction to use L'Hopital's rule. Specifically, you have to have a fraction that's a 0 over 0 or infinity over infinity. Those are the only times you're actually allowed to apply L'Hopital's rule. So what I'm going to do, I'm going to bring one of these two things down to the bottom as its reciprocal. The easier thing. the e to the a. Because reciprocating that is just going to be 1 over e to the a, which is e to the negative a. So we're going to rewrite this as 2 minus the limit as a approaches negative infinity of a squared minus 2a plus 2 over e to the negative a. And now you can justify to yourself that you have the right type of form. The top is going to infinity. The bottom is going to infinity. E to the negative infinity is e to the infinity, which is very, very large. And infinity squared plus infinity plus 2 is also very, very large. So we definitely have an infinity over infinity type. And now we can use L'Hopital's rule and get 2 minus the limit as a goes to negative infinity of the derivative of the top, which is 2a minus 2, over the derivative of the bottom, which is negative e to the negative a. Still an infinity over infinity type. Technically negative infinity over negative infinity. So we use L'Hopital's rule one more time. And we get 2 minus the limit as a goes to negative infinity of the derivative of the top is 2. The derivative of the bottom is positive e to the negative a. And now we have 2 over something that's infinitely large, which is going to 0. So we end up getting 2 minus 0, which is 2. So this integral converges to 2. And that seems terrible. Probably not unreasonably something that could be asked. Okay. Trying to think about one other example of it. So, yeah. Okay, we don't have to do volume. We can wait until Tuesday, but if you guys are gonna see it on Monday, you'd be like, we could have talked about volume on Thursday, but would you like to see another improper example? Okay. Another one with infinity or another one of the type 2 ones we talked about earlier on in class? Infinity, okay. To infinity. Oh, I know what I would ask if I would. He's done some arctangent stuff, right? Okay. So yeah, let's make it suck. So let's say we want to find the integral from let me think for a second here. Yeah. That. Sure. Yeah, that's terrible, James. Yeah, okay, we're gonna make it really terrible. We're gonna make it from 1 to infinity of 1, then 5, not 5, I've already drawn that line there. Let's make it 11 over x squared plus 3. Yeah, that's awful. Cool. I wouldn't put it past anyone. So, first things first, limit as b goes to infinity of the integral from 1 to b of 11 over x squared plus 3. I should have brought out the 11. So in fact, let's do that. I'm going to rewrite this as the limit as b goes to infinity of 11 times the integral from 1 to b of 1 over x squared plus, we know it's a 3 there, but we might change it a little bit. So how do we find the antiderivative of 1 over x squared plus 3? Well, we know that the antiderivative of 1 over x squared plus 1 is the arctangent of x. We would expect this to be similar. And what I would probably recommend is just memorizing the slight variation. So the more general formula is that if you have the integral of 1 over x squared plus some constant squared, then the antiderivative is 1 over that constant times the arctangent of x divided by that constant. So here, what constant squared do we have? The square root of 3. So in this example, our a is the square root of 3. And the antiderivative is going to be, we have to write the limit. You have to write the limit every time until you actually take the limit. And then the antiderivative here is going to be 1 over root 3 times the arctangent of x over root 3 from 1 to b. And we plug in. We get the limit, b goes to infinity of 11 times 1 over root 3. I guess I could have brought out the 1 over root 3 as well, but I didn't. Arctangent of b over root 3 minus 1 over root 3. Arctangent of 1 over root 3. Okay, now, as b goes to infinity, b over root 3 still goes to infinity. So this is definitely going to infinity. And the arctangent of something that's going to infinity is closer and closer and closer to what number? Pi over 2. And then the arctangent of 1 over root 3 is something that I think that Del would expect you to know. That's going to be pi over 6. Because tangent of pi over 6 is equal to 1 over root 3. So the arctangent of 1 over root 3 is equal to pi over 6. So here we end up getting something terrible. We get 11 times 1 over root 3 times pi over 2 minus 1 over root 3 times pi over 6. Which I would leave that way, but if you wanted to simplify it, you could write it as 11 pi over root 3 times 1/2 minus 1/6. And then 1/2 minus 1/6 is just 1/3. So you can really write this as 11 pi over 3 root 3. Lovely. Not lovely, yeah.
Have you got the b over root infinity?
Well, where's b going to? No, I'm taking the limit as b goes to, right. What's infinity divided by the square root of 3? Right. So basically, if you have your thing that's going to infinity and it's getting multiplied by something, it's still either going to go to infinity or possibly negative infinity if the thing you're multiplying by is a negative number. Yeah. Just like if you add a constant or subtract a constant from infinity, it's still going to infinity. So this had been like, if this had been, so not very excitingly, but if I had said like the limit as b goes to infinity of the arctangent of, let's make it weird, b plus 2 over negative 7. Well, b is going to infinity. B plus 2 is still infinitely large. And something infinitely large divided by negative 7 is actually negatively infinitely large. So this limit's going to be negative pi over 2. Where am I getting these from? I'm getting these from the fact that the graph of the arctangent of x has horizontal asymptotes at pi over 2 and negative pi over 2. And the graph of the arctangent function looks like this. So that really we can see, oh yes, the limit as x goes to infinity of the arctangent of x is positive pi over 2, and the limit as x goes to negative infinity of the arctangent of x is negative pi over 2. That's how really the easiest way of just knowing what that limit is. That's how I know it. I'm not doing anything special other than thinking about, oh yeah, the graph looks like this. All right, 1019. We'll talk about volume next week.